Welcome to the Net Change podcast, part 2. If the particle is moving along the x-axis that we see here on our graph, and this graph is the position, this graph is showing velocity, right? So that's our graph of velocity. What's the position of the particle at t equals 12 seconds? All right, so the position at t equals 12 seconds, I'm going to move this here. There we go. Is it's starting at 0, right? So don't look at the bottom part here. It's going to be our displacement. So from 0 to 8 seconds, it moves 40 feet in the positive direction, right? We can find the area under that area of that triangle, and the area under the curve is our change in position. Area under velocity is our change in position. All right, so it's moved 40 feet in the positive direction, and then it's moved 10 feet in the negative direction, right? Just find the area of the triangle, because that area under the curve is going to give us position, because this is velocity. Oops, sorry, I wrote the wrong number. So 40 plus a negative 10 is going to give us 30. That's our position. Your position is the same as displacement, because displacement is just change in position, right? So it's moved 30, it's now at 30. Where's the position at t equals 12 seconds if s of 0 is 2? All right, so now it's starting 2 feet farther. So what do you think we're going to do with that 2 feet? Well, we're just going to add that 2 feet to the 30, and it's moved 32 feet. So if your starting position is not 0, you're just going to add that starting position to it. So your position is just displacement plus the starting value. All right, if their starting value is 0, then you don't have to add anything. If the starting value is something else, you'll add that. Distance traveled, we would just take the absolute value of that negative part. So the particle has actually traveled 50 feet, right? But its change in position, or its position, is at 32 feet if s of 0 is 2. Okay, so some important concepts there. And like I said in the previous podcast, if you have questions, don't understand something, write those questions down, and I can go over it with you. I can go over it with the whole class. Because if you have a question, probably somebody else does too. How many feet is the particle from its initial position? All right, so we have v of t. All right, so if we're looking for how many feet the particle is from the initial position, we're looking for displacement. And you're looking for its position. All right, so that means we're going to integrate our velocity function and evaluate from 0 to 7. Since we're not looking for position, since we're not looking for the total distance traveled, we're looking at displacement, we're not going to worry about where it's positive and where it's negative. We're just going to evaluate. So for total distance traveled, you have to make those negative areas positive. So you have to know where the velocity is negative and where it's positive. But for displacement, you don't need that. All right, so we integrate. We have negative t cubed divided by 3 plus t squared divided by 2 plus 10t. And then we evaluate from 0 to 7. All right, so if I plug in 0, I'm going to end up with 0. So that's why the minus 0 is there. I plugged in 7 and got a common need to get a common denominator if I want to add those. But if I simplify it, it's just going to be negative 343 thirds plus 49 halves plus 70. I just need a common denominator to add those together. And I think I did that over on the side there. Negative 6066 plus 147.6 plus 426 means it is moved in the negative direction, because it's now negative 119.6 feet away from where it started. Right, so a lot of movement in the negative direction. What's the particle's acceleration at t equals 2? Well, we have velocity, so just take the derivative. Derivative of negative t squared plus t plus 10 is just going to be negative 2t plus 1, and then I'll evaluate when t is 2. And so negative 3 feet per second. That is our acceleration. That's a review. Suppose that an object is moving in a straight line with a constant acceleration, a of t equals a. If the initial velocity of the object is v naught, and the initial position of the object is P naught, not P net, but P naught, what is the position function? Okay? So we're given some information here. We're given that acceleration is a. If we integrate a, we're going to have velocity. All right? So if we integrate a, we have a of t plus c. We're given some information that when t is 0, velocity is v naught. So I've plugged in v naught for v of t. I've plugged in 0 for time, and we solve for c. So we have v of t equals at plus v naught. There's our velocity curve. All right, now let's get the position function. I should say our velocity function. Who knows if it's curvy? But I guess even a line is a curve technically. And then let's get our position function. So we're going to integrate a of t plus v naught. All right, so that's going to be a of t squared divided by 2 plus v naught t plus c. And again, we solve for c. We know when time is 0, position is p naught. So we have a of 0 squared divided by 2 plus v naught times 0 plus c means p naught is equal, c is equal to p naught. And that means our position function is at squared divided by 2 plus v naught t plus p naught. So you might think, well, that's nice, but how could that help me? Well, if we're given initial velocity, you now know how to take that the family of functions and make it the actual function for velocity. Kind of gives you a little hint there. Yeah, you can solve for c, but if you got the initial value, if you got the initial velocity, notice that initial velocity is going to become the constant value on your velocity curve, and the initial position is going to become the constant value on your position curve. Your position curve. Right? So I think that kind of helps out a little bit. The back and forth thrill ride, doesn't that sound exciting? Back and forth, just going back and forth, moves with an acceleration of a of t equals 300 st plus 140 cos t. Find the position of the ride after t seconds if its initial velocity is 50 and its initial position is 0. All right, so that we have initial condition for velocity 0, 50, and initial condition for position 0, 0. All right, so we're going to integrate. So we have v of t, and this is in your notes. We just integrate, I believe. Oops, and I am not plugged in as the computer tells me, and I better plug in really darn quick before I run out of battery power. There we go. All right, so v of t equals the integral of 300 sine t plus 140 cos t dt. All right, we'll integrate that. All right, so whose integral is sine? That's going to be negative cosine, right? Right, because the derivative of cosine is negative sine. So the integral must be negative cosine, because I don't have a negative there. So v of t equals negative 300 cosine t, and then plus 140 sine t, and then plus c. All right, so we're going to plug in and solve for c. All right, so, well, what do you think is going to happen here? So v of 0 equals negative 300 cos 0. Now, notice cos 0 is not going to be 0. All right, so be careful on that. Not going to be quite the same as when I just had some x's. So plus 140 sine 0 plus c. All right, so, oops, and I forgot to plug in for v. 50. All right, so negative 300 cos 0, all right, cos 0 is 1. So negative 300 times 1 is negative 300. So I have 50 equals negative 300. Sine 0 is 0. So that's just going to be 0, and then plus c. So that means 350, that looks like 380. 350 is c. And just to save a little bit of space, I'm going to put it over here. C equals 350. All right, so now we have the equation for velocity, the specific one. Right? It is negative 300 cosine t plus 140 sine t plus 350. And now we're going to evaluate, or integrate and then evaluate. All right, so now we're going to find s of t, the position function. Oops, I'm a little close there to my integral. There we go. So I can put it equals in. And I also need a variable of integration, dt. Don't forget, by the way, your variable of integration, or you may lose points on the AP test. All right, so negative 300 cosine t. Well, whose derivative is cosine t? Well, that would be sine t, right? Sine, derivative of sine is cos. And so now it's going to be negative 300 sine t. And then this would be a minus 140 cosine t plus 350t, and then plus c, and we have to solve for c. So we're going to plug in. We have 0, 0 is the value, and it's not going to be 0 because of sines and cosines. So 0 equals negative 300 sine 0 minus 140 cosine 0 plus 350 times 0 plus c. Oops, and the c is completely off the screen. Actually, it's non-existent. All right, so sine 0, that's 0. The only one that's not 0 is the negative 140 cosine 0. That's going to be negative 140. And so if we add 140 to both sides, 140 equals c, which means our position function, I need a little bit more space. One nice thing, when it's full screen, I can just hit extend the page and not have to scroll like this. Oops. Or have that happen. Come on. Looks like we've got some stuff written on the page. Well, look at that. Ta-da, I guess that didn't get erased. So, let's see if it matches. And it does. All right, so P of t is negative 300 sine t minus 140 cosine t plus 350t plus 140. That would be our position function. So notice we just integrated and we solved for c, and we just did that twice, right, to go from acceleration to position. I left this one up here. Find the antiderivative f of x. Find the antiderivative f of x of little f of x equals 8x. I have a screen recording box I don't think you can see that blocks my vision. Cubed. It's going to get squared. Plus 6x. That satisfies the condition f of 1 equals 6. All right, so if you're finding the antiderivative, it means you're going to integrate. And f1 of 6, f of 1 equals 6, that's our initial condition, if you will. Our initial condition does not have to be when something is 0. It just has to be some point on the original function so we can solve for c. So f of x equals 8x cubed plus 6x. That is the derivative. If we integrate, we get back minus our constant, but we can solve for the constant. So when we integrate, we have 8x to the 4th divided by 4 plus 6x squared divided by 2 plus c. All right, so that simplifies to 2x to the 4th plus 3x squared plus c. And then I plug in 1 for x and 6 for f of x, and that means that c is 1. So the function whose antiderivative, the function whose derivative is 8x cubed plus 6x and goes to the point 1, 6, that would be 2x to the 4th plus 3x squared plus 1. That would be the specific function. Okay. Let's look at another one. You gotta love the up and down writing on this one. A model rocket blasts off, and maybe it's blasting off, my writing's blasting off, and experiences an acceleration described by the function a of t equals 16t minus 6t squared, where a of t is in meters per second squared. Find the velocity if it's moving upwards at 3 meters per second at t equals 1. Be very careful. They will not necessarily tell you when velocity is positive or negative. If it says velocity is, if the thing is going up, your velocity is positive. Or the thing is going to the right, velocity is positive. If it's going down, or to the left, velocity is negative. So here, it's moving upwards, means velocity is a positive 3 seconds. It's not going to, if it's going downwards, it's not going to say velocity is negative 3. It's up to you to figure out that velocity going down is going to be negative. Okay? That's where you got to put your brain to use. All right, so we're going to integrate. We want v of t, and we can get v of t by integrating 16t minus 6t squared dt, and then solving for c. So v of t equals 16t squared divided by 2 minus 6t cubed divided by 3 plus c. So v of t is 8t squared minus 2t cubed plus c, and we have the moving upwards at t equals 1, so 1, 3. All right, so 3 equals 8 times 1 squared minus 2 times 1 cubed plus c. So that's 3 equals 8 minus 2 plus c. That's going to be 6. Right, 3 minus 6 is going to be a negative 3 equals c. And therefore, I'm looking for a spot to write this. I'll put it over here. V of t is 8t squared. Now my shadow was blocking me. Minus 2t cubed. I have to keep bending out of the way. And then it was plus negative 3. Yes, minus 3. All right, so there's our specific velocity function. And that's how you'll find it, is by integrating and then substituting the point and solving for c. All right, moving along. I got a feeling this is going to be at least 3 podcasts. The figure, a accompanying figure shows the velocity v equals f of t of a particle moving on a coordinate line. When does the particle move forward, move backward, speed up, slow down? When is the particle's acceleration? Oh, let's answer one question at a time. Let me read one question and answer one question. All right, so we're given velocity. When does the particle move forward? All right, well, it's moving forward everywhere and I think this one's in your notes, everywhere your velocity is positive. So right there, so from A is from 0 to 1 second, and then again from 5 to 7 seconds, right? Our velocity is above the x-axis. We're moving in a positive direction. All right, so that's the first part. Oh, so I should probably write what this is. This is move forward. Moves forward. Moves backwards. All right, so anywhere the velocity is negative, it's moving backwards. So it's moving backwards from 1 to 5. Now, if this were, and I was taking the AP test, and this were a question, I would say, and actually I'm going to add in, because this is not a very complete answer. So if this were a question on the AP test, I would add a little bit more. Let's add a little bit more to our notes. Let's add the why. It moves forward because velocity is positive. Let's give better answers here. Sorry, that's me. I did not put a better answer. We should put a better answer. That's a better answer. All right, and then from 1 to 5, the particle moves backwards. You probably should make this a full sentence, but these are notes. Moves backward is okay. Because we got the because in here. Because velocity, what is this, like Tarzan talking this? Because velocity positive. Ooh, me Tarzan. Velocity positive. Velocity is positive because velocity is negative. What a horrible sentence that was above. All right. Speed up, slow down. All right, so these are slopes, right? So wherever my slope is going to be negative, right, I'm slowing down, right? Because we've got whatever the y value is, that's the slope, right? That's the velocity, that's the speed I'm going, right? So at t equals 0, I don't know what number that is because there's no numbers on the y-axis. Maybe that's 3, right? And then maybe at 1 I'm at 0, right? So clearly I'm slowing down, right, from here to here. I'm going to erase these lines. So clearly I'm slowing down from here to here, right? Slowing down. But I can't really say I'm slowing down from 1 to 2, right? Because I was at 0 and I'm going faster. I'm just going in the negative direction. So from 0 to 1 we're slowing down, right? Because the value of velocity is decreasing, right? Until we get to t equals 1, and then we're at 0 seconds. So let's write that in. We're speeding, or I did slowing down first, sorry, it said speeding up. So we're slowing down from 0 to 1 second. And let's add all the other places, so I have to keep writing this down. All right, so we're also slowing down here, right? Because I was going let's say this is 5, right? Let's say that's -5. So I'm going 5 meters per second, right? I'm just going in the negative direction. And then maybe I'm going 4 meters per second. And then all the way till 5 when I get to 0. All right, so I'm also slowing down there because I'm less negative, right? I'm moving in a negative direction and my velocity is less. Oops. So from 0 to 1, and then from 3 to 5. Right, and then I'm speeding up because anything is faster than 0, right? And then I'm slowing down here as well. And then 6 to 7. And let's just say it this way, because absolute value of velocity is decreasing. I think that's a better way to say it than just velocity is decreasing because, well, -5 is more than -3 is less than -3, right, technically. But in terms of velocity, you're going faster. You're just going faster in the negative direction. So I think it'd be better to say the absolute value of the velocity is decreasing so that we're more specific. So, boy, we got lots of this part 1 here. My A is taking up my entire page. I'll write smaller and squeeze B and C in there. Where the question is. All right, and then we're speeding, so I should probably put little bullets so you can see one from the other. And then we're speeding up, well, on most of the other spaces, right? We're speeding up, I'll use blue here. So I'm speeding up here from 1 to 2. Oops, I was trying to fix my P. Looks like speeding up. We're speeding up 1 to 2. And then from 5 to 6. Because the absolute value of velocity is increasing. All right, so let's go on to B. Oh, we finished A. So like I said, if you have questions, ask me about this in class. B, when is the particle's acceleration positive, -0? All you have to do is look at the slope of VT. All right, so that will tell you when the acceleration is positive. So when our acceleration is going to be positive if our velocity has a positive slope, and it's going to be negative when our velocity has a negative slope, and constant, 0, when the slope is a constant value, right? It stays the same. We have a horizontal line. All right, so we have a positive acceleration. From 3 to 6. And that is it. And that's because v of t, the velocity, has a positive slope. I'm going to put a plus, all right, for positive. So I can kind of squeeze this in. Positive slope. We have negative acceleration. And I'm going to, I don't know, maybe I should put like a line here so that those two answers don't run into one another. It's taking up a lot of space for me to write. Negative acceleration. Maybe if I write smaller. It's a little hard though with these markers. Negative acceleration from 0 to 2 and from 6 to 7. And that's because I can't even fit v of t, has negative slope. Should move my line a little bit further down. There we go. And then where is it 0? It's 0 from, I'm just going to put, I'm going to abbreviate, acceleration. I should have done that. Acceleration is 0, and that's from 2 to 3, because v of t, the slope, has 0 slope. I don't know. There must be a better way to squeeze all this in. I think writing smaller initially would have helped. I can't even extend the page, or I won't be able to see the questions. When does the particle move at its greatest speed? I'm not sure, to tell you the truth, because there's no numbers on here. It's one of two things. It's either here, so this is for C. It's either here or it's here. All right, so I can't tell which number looks greater to me. So it's either 1 or 2. Whichever has largest absolute value. All right, I can't, without numbers, I can't tell. All right, so I can't tell if it's at t equals 2 seconds. That's why I put the 1. So it's either 2 seconds or I guess I should put 0. I put a 1 or 2 just to highlight where I was talking about. But the time I'm talking about is either t equals 0 or t equals 2. All right, and whichever has the greatest absolute value. So this is my answer to C. All right, so that's, the red is C, and B is the blue above the red line, and A is everything else. And then D, when does the particle stand still for more than an instant? Standing still, not moving at all. Nowhere. It's not standing still from 2 to 3 seconds, right? Its velocity is just staying at, I don't know what that number is, 4, 3, 2, who knows, because there's no numbers on the y. But it's never standing still for more than an instant, right? It's constantly moving. Oh no, I'm sorry. didn't see this part right here. See that part right there? I didn't see it. I'm looking, I'm going down, down, down. Whoops. So from 7, so here's the answer for D, from 7 to 9 seconds, because V of t equals 0. Okay. I shouldn't have written in sentences, I guess, for A. It took up so much space. All right, so let me know if you have questions on this one. Perhaps you can write this a little neater than I have. I'm probably going to get stuck rewriting this again, but I guess that's okay for now. I'm going to have to end this tape. I told you that there'd be at least one more. All right, so I'll be back in the next podcast. Bye.